Okay, today's video is IGCSE Physics Edexcel International. So paper 2 is coming up, I think, in early June, and this is last year's regional paper. So when it's regional, they put an R next to the paper number. So it was done last June in countries outside the UK, so R stands for regional. And this is a follow-up to paper 1, which was done last week, I believe. And I did a prediction video based on the questions that came up in paper 1 to try and work out what they hadn't asked about. So go and watch that video and have a look, and then I'll give you a run-through of last summer's regional paper. Unfortunately, I haven't seen the non-regional paper, paper 1, so I can't do a prediction video for that, okay? Now, the prediction is basically based on which topics didn't come up, yeah, or subtopics. So we're just going to go through this one, and then I'll make a comment as to what I feel they will do for paper 2, okay? So the first question is about stars. So it's from astrophysics, which is topic 8, okay? So it's a Hertzsprung-Russell diagram. And the first thing they want you to do is to label the axes. So the y-axis is the brightness, which officially you should put as luminosity. So luminosity is the same as the power output of the star. It can also be labeled as absolute magnitude. So it's basically the brightness if they were all the same distance away. And that's what absolute magnitude means. So it's a way of doing a fair comparison in terms of their brightness. You can't put brightness, so luminosity is correct. Okay, you'll see that the sun is around there. Okay, so that will be this will be the luminosity of the sun here. Okay, and the temperature of the sun here is about 6,000 Kelvin. So the other axis is 6,000. Okay, so the other axis is temperature. And of course, normally they would do the temperature in Kelvin. They haven't asked for the units, they just want you to label the axes in terms of what quantities are in a Hertzsprung-Russell diagram. Okay. There are 3 shaded areas on the diagram. Yeah. So you can see the 3 grey zones is what they're talking about. And you've got to name the shaded area that contains the sun. So I've shown you where the sun is, and these are the main sequence stars. Okay? That means they're in the phase of their life cycle where fusion of hydrogen occurs. So that's the main part of the life of a star, nuclear fusion, hydrogen. Okay, so you get 2 marks for the axes and 1 mark for knowing that what the main sequence is on a Hertzsprung-Russell diagram. Okay, so I think in 2025 they will probably talk about stellar evolution. So what is the something like this question, but ask you to potentially explain the phases of the life cycle of stars. In other words, they go from protostars, almost stars, and then how do they form into, when do stars start fusing hydrogen? Yes, so that's the main sequence stars. Then what happens to them when they run out of hydrogen? Then the red giant phase, yeah. And then after that, it depends on the size of the star, whether they become a white dwarf or something like a neutron star if they're much, much bigger. So supergiants rather than red giants. Now, what could be also asked about is how does a protostar trigger the nuclear fusion reaction? And that could be linked with the kinetic theory from the pressure section, Unit 5, solids, liquids, and gases, because protostars are made of plasma, and the density increases, and eventually that makes a pressure increase, which increases temperature, and then you've got a critical temperature to create nuclear fusion. And we're talking about tens of millions of degrees in the core of the sun. Okay, so they could link astrophysics with a kinetic theory of gases. So which star is a white dwarf? So that's the star which is labeled B, because it's always the bottom left on the Hertzsprung-Russell diagram, which is what our sun will become when it eventually is unable to do any fusion whatsoever. Okay, so the white dwarf is here. Okay, and then it says, at a standard distance, obviously from the Earth, which star is brighter on the diagram than the sun and has a greater surface temperature than the sun? Okay, so brightness at a standard distance is the definition of absolute magnitude. Yeah, and that's a fair way of comparing the luminosity of a sun. So we're looking for C, and we'll have a look at the diagram now. Why is C brighter than the sun and has a greater surface temperature? Okay, so that's something that we need to look at on the axis. So C is brighter because brightness increases up the y-axis, and temperature increases in the opposite direction on the x-axis. So here is about 3,000 Kelvin, then 6,000, then 12,000 would be around here, and it's non-linear, and here could be around 24,000. So it keeps doubling. So both axes actually are non-linear. Okay, so you need to know this about the temperature axis, is that the temperatures to the left are greater than to the right. Yes, so that's why C has a greater surface temperature than the sun, 6,000. So based on the approximate values of temperature I've put, the star labeled C will be between 12 and 24,000 Kelvin. Okay, so now you've revised the Hertzsprung-Russell diagrams. What else could they ask you in astrophysics? So in 2025, they could ask you about evidence for the Big Bang, because this is something that only gets asked about in paper 2 content. Yeah? Whereas the brightness of stars can come up in paper 1 or paper 2. Okay? So here's the mark scheme for question 1, which we've been through, as alternatives that you can put. For example, on the x-axis, instead of putting temperature, you could put color or spectral class. They'll accept that, but normally we do use temperature on the Hertzsprung-Russell diagram. And as you know, temperature is related to the color of a star, and so the spectral class is also linked to the temperature. So they're being generous in that respect. Okay, I'll let you stop the video and have a look at the rest of the mark scheme. First question done. Question 2 is about nuclear fusion and fission. Fission and fusion. Now, fusion could happen in stars. So this is topic 7, which is nuclear physics or radioactivity. Okay, anything to do with the nucleus. The table gives some statements about nuclear fission. Yeah, these statements could be about nuclear fission, fusion, or both. And you've got to place ticks in the columns to decide which statement is describing nuclear fission and which statements describe nuclear fusion. So requires high pressure and temperature, and that's what I'm saying is something that they could ask about in the 2025 paper, because not much has come, nothing came on that in paper 1. Okay, so nuclear fusion requires high pressures and temperatures for it to overcome the repulsion between protons. Okay, basically the nuclear fusion process starts with protons bumping into each other, colliding with enough kinetic energy to overcome the repulsion of the electrostatic forces between them. And energy is released in the process. So we know that nuclear fusion releases energy, but so does nuclear fission. Okay? So both fission and fusion release energy, but only nuclear fission produces daughter nuclei. Yeah? Nuclear fusion is joining two nuclei to make a bigger nucleus. Okay? A more energy efficient one, you could say. So then part B is talking about nuclear fission reactors and how they use control rods and moderators. And you need to know all the parts of a nuclear fission reactor. You've got to describe the function, in this case, of the control rods and the moderators. So the main job of the control rod is to absorb neutrons, because if you have too many neutrons produced, they can create a chain reaction, yes, and that can be dangerous. If a chain reaction gets out of control, the energy produced could be too great, and you need to keep it from getting too high a temperature. And moderators are used to slow down the neutrons, because neutrons that move too fast actually are not very effective. So you need to moderate them and absorb some of them, so you just got the right amount to maintain a constant energy supply to produce the steam to turn the turbines. So what could they ask in 2025? Yeah, they could ask about nuclear fusion. How does fusion occur in stars? So I'm saying that this, again, can be linked to pressure, density, and temperature, and they could link this to the kinetic theory of gases. So this is one of my predictions, is that in 2025, in the regional paper, because they haven't discussed kinetic theory, that they could link it to star formation, okay? And the triggering of nuclear fusion. So you can see how thermodynamics and astrophysics are linked, yes? So this is thermodynamics, the science of energy internally in gases, for example, okay? And plasma is an excited form of a gas. So these are the these are the marks that they will give you for the question we just went through, 5 marks for question 2. Okay, you can see paper 2 is not necessarily more complicated, but there are certain things that they don't ask in paper 1 because double science students haven't studied them. So here you got liquid gallium, yeah, which is allowed to cool in the laboratory. So we're talking about changes of state. So that's solids, liquids, and gases, which is where the kinetic theory also comes in. So they want you to complete the diagrams by drawing the arrangement of particles in a liquid, yeah, and a solid, and you have to draw them carefully. Okay, the first particle has been placed in there for you. I haven't drawn it, but you need to make sure that the liquid, the particles are randomly arranged. It's not a rigid structure, whereas the solid are regular arrangements. So you need to draw all of the particles the same size, which is also why I didn't bother to draw it. But you've got to draw them, all the particles the same size, and both of them are in contact with each other. Yeah, equal in size, in contact. These are irregular and these are regular. Okay? Now you don't have to fill the liquid one, but normally a solid one would be filled in the whole square. Okay? So they haven't drawn it in the mark scheme, so we're going to have a look at the mark scheme afterwards. Then they say the initial temperature of the sample of gallium was 80 degrees centigrade. So I put that as my starting temperature on my temperature scale. And then the freezing temperature, they say, of gallium is 30 degrees centigrade. So, for example, if you hold some gallium in your hand and your skin temperature is slightly above 30 degrees centigrade, you can see that the gallium will melt in your hand, okay? And then the final temperature as it's cooling, it will be 20 degrees centigrade, probably because that's room temperature, maybe. So that's an assumption I'm making. But complete the graph to show how the temperature of the gallium changes during the time it cools to 20 degrees centigrade. So the main thing is at 30 degrees centigrade, it freezes. And while it's freezing, you run a horizontal line. So the freezing portion will be a marking point that it's going to be horizontal. And then the cooling bit here could be a straight line or it could be a curve. Now normally it will be a curve because obviously the greater the temperature difference, the faster the rate of cooling. Okay? So I've kind of drawn a half curve, half straight line. Yeah, it's probably not very well. And then afterwards, it's going to be more of a straight line because the temperature difference isn't very high between 30 and 20. So while it's freezing, temperature will stay constant. When it's all frozen and it's gone into the rigid form of the solid that you drew in part 1, yeah, or part A or whatever it was, then it will cool eventually to room temperature or the surrounding temperature. Okay, and then it will stop. They don't want you to go beyond that. So I put a zigzag line here to show that I don't need to go below 20 to 0, for example. Okay, so that's how you do this question. So I think in 2025, from this topic, they will ask you about specific capacity in some respect. And that's the equation energy input, or delta Q sometimes, equals the mass times the specific capacity times the temperature change. And they could then link it with a power supply, electrical power supply, to heat an immersion heater, yes, and to then this multiply by how long they keep the immersion heater on is the energy supplied to whatever they're heating. Could be water, it could be a metal block, and they'll give you a problem about linking power input in time with the temperature rise and ask you to work out one of the variables in the first equation. So this is another prediction I have, is that they're going to give you something like this in paper 2. Okay, you should definitely be ready for it. Now there is a video which shows, this is a core practical. In one of my playlists, check the playlists, it's got exactly what you need to know for this core practical. Okay, like how you do the experiment. So they could give you a question on this precise experiment. Okay, they could also give you another change of state graph like this. So these are quite common in paper 2. So change of state or specific capacity. So question 3, the mark scheme is here. I'll let you stop the video if you want to go through it. Question 4 is now about transmission cables and how long distance transmission of electricity takes place in the national grid. So this is from electromagnetism because you need to use transformers, step up and step down. There's a link with topic 4 energy, because in topic 4 energy you also have to study energy resources. Okay, now they haven't talked about what the power station is burning, so it's more topic 6 than topic 4. So they've shown a power station and a school, and they want you to add to the diagram by drawing, and that's the key word, structures needed to efficiently transfer energy from the power station to the school. So we're going to go from the power station to the school. Obviously you need pylons and cables, but they want you to know that you need a step-up transformer. And the drawing they want you to include, they want the coils shown that you have a low input number and a high output number, and then the reverse of that they want you to draw again here. So you've got to draw it twice, step up and step down, and label it thus. So here the coils turns, the coils, this is meant to say coils reverse turns ratio. So if this steps it up, say, I don't know, 100 times, this one will be stepped down 100 times. So you need to draw a second transformer there and draw the coils as well. Okay, so it's important to clarify that they want it drawn, not just a block diagram saying it's a step-up transformer. So I wouldn't get the full marks because I've only drawn one of the transformers, but I would get a mark for labeling step up and step down. So then they want you to explain how the amount of current in the cables increases the efficiency of the transmission of electricity. So obviously we don't want to produce heat. So a low current creates less heating. The heating effect in cables will be less because the heat produces P equals I squared R. So they want you to know that low current produces less heating. So that's why we do a step-up transformer, because by increasing the step-up transformer increases the voltage. Yes? So that's, they want you to see if you know that in the cables, okay? So that you can transmit the same power can be transmitted, but at a lower current. Therefore, with less heat energy transfer or lost to the surroundings. Now, they want you to have the keyword energy in there. They don't want you to concentrate on heat alone. So you need to have the keywords energy transfer to the surroundings will be minimized. Okay, another keyword that you could use, less energy dissipated. What does dissipated means? Given out and spread out. Okay, so what they haven't given us is a calculation for transformers. So in 2025, make sure you know how to do the transformer calculations in terms of the turns ratio and in terms of efficiency. So we want to also understand the efficiency can be given as power in and power output. Okay, so also efficiency. So efficiency calculations, transformer turns ratios could be asked about. Okay, so if the voltage goes up, the current goes down by the same amount. So the power in should equal the power out because they're more or less 100% efficient. Okay, here's the mark scheme for question 4, 6 more marks done. Okay, question 5 then is about momentum, forces of momentum for topic 1, but they also ask about kinetic energy, which is topic 4. So the diagram shows collision between two balls, A and B. The masses and velocities are shown before and after the collision. Here you got before, here you got after. Yes, so before only ball A is moving, and then ball A hits the bigger ball B. Ball B is not moving initially. So when it hits the bigger ball B, or massive ball B I should say, it rebounds. So if we count this direction as positive, then this direction will be negative. And remember, momentum is a vector quantity. Okay, so when the balls collide, ball B applies a force on ball A to slow it down. Yes? So it causes the velocity to change by decreasing it. Okay, but ball A also applies a force on ball B to start it moving in the positive direction. Okay, so this is Newton's third law, equal and opposite forces. So describe how these forces on A compare with the force applied on B. So this is Newton's third law, which means the two forces are of equal magnitude but opposite in direction. Now you got to make sure, I'm just talking, so you got to make sure when you write it, you don't leave any gaps. So you got to say the forces must be of equal magnitude but opposite direction because they're a Newton third law pair of forces. And that means when it's third law, the same force is interacting at the same time on two objects. Okay? So Newton's third law is about two objects, and it's about an interaction between two objects, and the forces on them are exactly the same size but exactly opposite in direction. Now they want you to calculate the momentum before the collision. So only ball A had momentum, so they want to see that you know how to calculate momentum. This doesn't come in paper 1, so you've got to give your answer to the correct units. If you calculate it to 3 significant figures, it becomes 0.882. but since the data is only accurate to two significant figures, you can change it to 0.088 kilograms per meter. Kilograms meters per second. So this is a good preparation for 2025 because we haven't had one of these, obviously, because they can't come in paper one. So you always got to be ready for conservation of momentum. Now, we haven't done conservation of momentum yet. We've just done momentum, initial momentum. Okay, then you've got to show that the velocity of ball B after the collision is about 0.6 meters per second. So you want to show that it's about that, which I've done, but I forgot to link it to the show that. Show that means, if they ask about show that, it means you've got to prove it mathematically. Okay? So momentum must be conserved. So we know the total momentum before because they helped us by making us work that out to start with. So we know to three or two significant figures, it was 0.0882 if you go to three significant figures. Then momentum of A reverses. So this is negative. So you've got to put the negative there when you put the numbers in. And momentum of B is then in the positive direction. To the right is positive. Okay? So you put the values in. We know the momentum before. You put the mass of A multiplied by the velocity of A, but in the negative direction, so outside the brackets. And then we know the mass of B, but we don't know the velocity of B. So the only unknown is VB. Now, if you can change the equation around to make VB the subject, you'll probably get a mark for doing that. Put the numbers in, do the algebra, you'll see it comes to 0.571. To two significant figures, 0.57. And to one significant figure, it is actually equal to what they asked us to show. And show that means go back to the question and show that you understand what you're doing. Okay? Go back to the question. All right, part D. It then goes into kinetic energy. Collision is considered elastic if the total kinetic energy is conserved. That's what it says in the brackets. Before the collision is equal to the kinetic energy after the collision. Okay, the total kinetic energy. So total kinetic energy you can work out, okay, using half mv squared. So that's the values before, okay. So the mass is 0.018, half of that, yes. So half the mass is there, multiplied by the velocity before. It gives you the kinetic energy you started with. So now we've got to see, is the kinetic energy after going to give you the same number? So this time you've got two objects moving, and this time the direction doesn't matter because kinetic energy is not a vector, it's a scalar. So the A and the B kinetic energies need to be added up again. Half the mass times the final speed squared for A, and then half the mass times the final speed squared for B, which we did in the previous part. Okay, so you put that number in here, and you notice that 0.110 was after for ball A, and for ball B it was 0.0432. When you add them together, it is still less than the kinetic energy before, which was 0.216. Therefore, the collision is not elastic. 99.9% of collisions are not elastic. The only time you may get something close to elastic collisions is with microscopic atomic molecules, atomic collisions, okay? So this is, again, a very good revision for 2025 because this is the kind of question they cannot give in paper one. So you should revise these kind of questions. There's quite a few paper ones in my playlist. I haven't done many paper twos, but I will try to add some. I only started doing GCSE questions at the end of last year. So I've added GCSE Extra, and if you find these videos useful, don't forget to share them with your classmates, because unless I get enough views, I will go back to doing A-level videos because I originally started with A-level videos. Okay, so that's question 5, and here's the mark scheme. Okay, A and B, C and D. 12 marks. Okay, also if you have any requests, you can leave comments underneath the video. Don't forget to say please and thank you, because that makes it more likely that I'm going to respond. And make sure you like each video that you found helpful. Don't just watch them without giving a like, because that's how YouTube works. Unless we get likes and subscribers, then the channel will discontinue eventually. Okay, so the next question is from topic 4, energy resources, which comes up in every year more or less. You need to know something. This is about generating electricity from renewable energy resources. So they want you to know the difference between renewable and non-renewable. But in this case, they are comparing a solar farm in the UK, which is on the left, with a geothermal power station in Iceland, where they got a lot of geothermal energy, heat coming out of the ground. So geological reasons. So they want you to discuss, and this is a very common question for this energy resource topic, discuss the advantages and disadvantages of solar versus renewable. So advantages I've put as a plus. You should put the word out, and disadvantages put as a minus. So basically, I've put a grid, 4 marks, and you've got to have 1 point in each grid. So you can see what I've done. Geothermal works day and night, whereas obviously solar only works in the day. So that's obvious comparison, because discussion means speak about both sides. The other disadvantage, which I didn't put first, is that it requires a large area of land, solar panels. You can see in the picture how much land is taking. And of course, that land is not that green because you've got solar panels on it. Whereas before it could have had grass, plants, and plants themselves are a method of taking in carbon dioxide. So you've got to be careful that it's not as simple as people make out. So here it says no greenhouse gases are emitted in solar, which is one of the things you need to know about as an advantage that they want you to know about using non-fossil fuels energy resources. But of course, there is energy required to make the solar cell. So when you're building it, you probably used oil to use the energy to build them. So you probably have created some greenhouse gases in the construction phase. But so that's why I put no greenhouse gas once built. Okay. So then the other box is the disadvantage of geothermal. It may release some polluting gases. It could release from the ground sulfur dioxide or ammonia or whatever. It doesn't have to be linked to carbon dioxide. Okay. Now there's alternatives if you look at the mark scheme. I'm just saying that's how they're going to give you the 4 marks. 1 advantage for each, 1 disadvantage for each. Discuss means don't just bullet point it. Talk about the differences between them. So you may need to pad it out a bit. So here's the mark scheme. Advantages, disadvantages. I'm not going to read through them. I'll let you stop the video and see if you've done the paper, whether you would get the marks or whether you've laid it out in a clear enough manner. Okay? Remember, when I'm going through these videos, I'm not writing it out as a model answer necessarily. I'm explaining to you the kind of things you need to include to get the marks. You then need to put it in through the format that the examiner will be pleased with. So here a student investigates the amount of light affecting the output of a solar cell, the voltage output of a solar cell. So this will be a voltmeter here, and they're looking at the distance of the light source, in this case a normal lamp, the distance to the solar cell, and so it's really about the scientific method. So scientific method will definitely come up it could be about anything in your paper too. So the student varies the distance between the solar cell and the lamp, so that's your independent variable, and then he has to measure the output voltage, each time he changes the distance. So therefore, that's the output voltage of the solar cell is the dependent variable. Here's his results. He's just written them down as a list: 5 centimeters, 8 centimeters, 11 centimeters, 14, 17, and so on. Yes, obviously as the distance increases, the voltage produced by the solar cells decreases. Now you can imagine that not all the light doesn't go towards the solar cell. It's going in all directions, okay? So obviously a lot of the light is lost. It doesn't actually activate the solar cell. So the intensity of the light is diminished because it spreads out in all directions. They just want you to draw the table and put the results in a table. So they will give you a mark for putting the quantities, distance, and output voltage. You need to put the relevant units for the second mark and include all the data as given. That means get the same number of decimal places that they've put, that the student had here. All you got to do is transfer it. So it's a scientific method. And then they want to ask you about a control variable, yeah, for this experiment. I put the brightness of the lamp used. Yes? So you want to keep the same lamp throughout, and you can look at the mark scheme for alternatives. They just want you to know the scientific method. The student states, so now they're going to the conclusion. Students state that the solar cell could be used as a power source for the lamp. Okay? This suggests, they suggest that this would work if the solar cell is connected directly to the lamp. In other words, the voltage created by the solar cell is then feeding the lamp to make the lamp work. Okay? The light from the lamp is used to produce the output power from the solar cell. In other words, you're creating an energy cycle, if you like. But you've got to explain, with reference to the principle of conservation of energy, why the suggestion would not work. So the key points you need to add in your explanation is the energy transfer will not be 100% efficient. Okay? And then for a start, not all the light, even if you could light it with the solar cell, reaches the solar cell because it's radiated in 360 degrees. Yes? So not all of it reaches the limited surface area of the solar cell. And also the solar cell, you want it to be at right angles to the light coming in. So it's not that simple. And there'll be other energy losses because you've got electricity for a start, and you've got heat losses. So you've got to add depth, detail, and clarity. And these 3 bullet points will definitely get the 2 marks as long as you've explained it clearly. Okay? Have a look at the mark scheme. How you tabulate it. Distance in centimeters, voltage in volts. Consistent number of decimal places here. Key points here were there were no decimal places there. The student could have measured it more accurately. He could have put, I've measured it 5.0. Yes? He could have shown that. That would have been an improvement. They haven't gone through evaluation, but that could have been an evaluation point. And that's the question done. Question 7 is from the topic on waves. And waves, it's in paper 2, sound is more of a topic than it is not really covered in paper 1, except that you know that sound can be reflected and refracted. So the students are doing an experiment using this wall, which is exactly how I used to do it. Yes. The students are going 100 meters away, which is exactly the distance I used to use when I used to do this with my GCSE students. So the sound is being produced by the students. It goes there, and then it comes back to them. So it goes 200 meters by the time it's gone there and reflected back. 200 meters. So what they're doing is they're hitting wooden blocks together or something to make a sound, sharp sound. You want a sharp sound to have a clear echo. Yeah? So they continue to hit the blocks together every time, as soon as they hear the echo. So they're using a rhythm method to synchronize the hitting of the blocks with the hearing of the pulse return. Yes? The sound pulse, the sound echo return to them. and this other student starts the timer and ends it, the timer, stops the timer after 20 echoes have been heard. Okay? So basically it's gone 2 times 100, 20 times distance. So in that time, the sound has gone backwards and forwards 2 times 100 times 20 meters. Okay? Give a reason why they don't stand any closer to the wall. Well, the time would be too short, and therefore it would be difficult to measure accurately. Yeah? So it's a question of accuracy and human reaction timing. So these are things you've got to consider. You want to get the time to be as long as you can, but it's also got to be practical. So here's the data. They repeated it 5 times, and you notice that one piece of data is different from the others, which are in a very narrow range. So if you take out this anomaly, you'll see the mean is 11.64. Sorry, if you include the anomaly, it's 11.64. If you remove the anomaly, the mean would be 11.76. So it depends how you decide to use your data. So circle the anomalous result in the table, 1 mark. Suggest a reason for the anomalous result. Maybe they miscounted the 20 hits one time that they repeated it. Maybe it was 21 or whatever, yeah? Or was it less? So maybe it was 19 echoes that they measured by mistake. So they could have miscounted. But you can give us something alternative. As long as it's common sense and logical, they'll give you the mark. Look at the mark scheme. Calculate the mean. They haven't told you how. So with the anomaly, 2 decimal places will get you 2 marks. And without the anomaly, it gets you the 3rd mark. So if you notice an anomaly and you definitely don't want that data, you can eliminate it from in your scientific method. It's valid to do that. Okay, so if you get the 11.76, be careful the rounding up. If you don't use the accurate calculator value, you might get 11.75, which will lose you a mark. So the 3rd mark is for how well you do the averaging. Okay, so then the speed of sound in air can be calculated using the distance traveled. Remember, it's an echo, so it travels there and back. And the time should be divided by 20, or the distance should be multiplied by 20. I multiply the distance by 20 and divided by the time for 20. And that gives me an accurate value, although possibly not valid to quote it that accurately. That's 5 significant figures. If you do the time for 1 hit and back, you could divide the mean time for 20 by 20. You'll get the time for 1 echo as 0.59. So you can do it either way. And then you round it up to 2 or 3 significant figures. It will give you the same value. Okay? So you should limit it to 2 or 3 significant figures. Okay. Hope that makes sense. That's 9 marks done. So sound will definitely come in 2025, but not necessarily in this format. It's more likely to come as an oscilloscope. Here's the mark scheme. Question 8 is back to electromagnetism. This is a force on a moving charge, and the moving charge is a proton. So it's a machine that can be used to measure the speed of fast-moving protons. Okay? So this is something that you will do in A-level as well. So it also includes topic 2, knowledge of charged particles. Okay? They've got a negative plate here with a hole in it. And the proton is accelerated towards the negative plate because opposite charges attract. Okay? And the proton will go in here because there's a magnetic field. It produces circular motion. The path of the proton goes in a circular path. Okay? So this is Fleming's left-hand rule. Because if you think about it, a moving charged particle, positive, is like the direction of current flow. Because remember, current is the rate of flow of charge. And a proton is a flow of charge, a movement of charge. At the start, the proton is attracted towards the negatively charged plate. Give a reason why the proton is attracted to the negatively charged plate, because they are oppositely charged. Protons are positive. That's what they want you to say, opposites attract. But, they could also, in 2025, I put a note here, they could use this motor effect, because basically causing a proton to change direction is Fleming's left-hand rule, if you know the direction of the current. But you can also get the motor effect. So this is about, motor means movement. You can get movement in a loudspeaker or a motor itself. So the motor effect is Fleming's left-hand rule. So in 2025, they could ask you about loudspeaker or the motor effect. You need to make sure you've revised these and are able to use Fleming's left-hand rule to explain why a loudspeaker vibrates to make sound, and this one turns. Yes, one uses DC, one uses AC. Okay, so this could be a question to prepare for your paper 2 exam. Then it says the proton accelerates and gives you the acceleration from rest, so you know u0, to a final velocity which is quite fast. So they want you to work out the time taken. Well, we know the acceleration is change of velocity over time taken. If you change the algebra, you should be able to notice that t will equal the change of velocity divided by the acceleration. Since the initial velocity was 0, it's the final velocity divided by the acceleration given. That gives you a small time of less than a microsecond. 7.26 times 10 to the minus 6 seconds. I've given it to 3 significant figures, okay, which I think is valid because the data provided is 3 significant figures. So this is about, again, this is a show that, I forgot to mention that. Show that is about 7 times 10 to the minus 7 seconds. So you go from 3 significant figures to show that is approximately equal to 7. It then says the proton passes through the hole that I've mentioned before in the negatively charged plate, where it enters the magnetic field, and it's normally a uniform magnetic field. The magnetic field exerts a force on the proton, so this is what causes the Fleming's left-hand rule. Manchester Football Club, MFC, the thumb is the motion, the first finger is the field, magnetic field, and the second finger has a C in it, so that's the current, and in this case, the current is the direction of the proton flow, the proton movement. This force causes the proton to follow a circular path, okay, without changing speed. So it's acceleration at constant speed. Why is it accelerating? Because it's changing direction. It may not be changing speed, but it is changing direction. So that means the velocity is changing. So they want you to use Fleming's left-hand rule to work out the direction of the magnetic field. And if you do it properly, you will see that it goes into the page. The symbol for into the page is that. Out of the page would be a dot in the middle of the circle, as if a dart is coming towards your eye, and this is as if the tail of the dart is moving away from you. Okay, that's the notation. Part 2 suggests how increasing the strength of the magnetic field will affect the proton when it's moving in a magnetic field. Where a stronger field means a stronger force, yes, and the stronger force means a greater acceleration. So if it's greater acceleration but the speed, without changing speed, it means the direction will change faster. So the radius of curvature will decrease. In other words, it will turn more suddenly. So it will hit the detector further to the left. If you go back to the diagram and have a look, yes, the detector is here. The black area is where you can detect it. So I've drawn the second situation. If you increase the strength of the magnetic field, it will hit here more to the left than the original path that they've shown here. Okay? So that's 8 Question 8, 7 marks done. And in 2025, they've given you a SUVAT equation here, which was A equals V minus U over T, and changed around. I think they're going to give you V squared equals U squared plus 2AS in 2025. So make sure you know how to use V squared equals U squared plus 2AS. By the way, it comes from this potential energy change into kinetic energy. Masses cancel out. And you'll see, if you change the equation, V squared will be equal to 2GH, where U was 0. If U is 0, 2 matches, A is G, distance is H. So for a falling object, you could just do potential energy equals kinetic energy. But I think, make sure you know how to use V squared equals U squared plus 2AS as a possible SUVAT equation that they could ask you about, because they didn't ask it in paper 1. There's the mark scheme. Okay. Question 9. This is what I was telling you. They're going to ask you about an oscilloscope. 9 times out of 10, this comes up. The oscilloscope has voltage on the y-axis, time on the x-axis. Each square is worth the value given on the oscilloscope settings. Basically, what an oscilloscope is a voltage graph plotter. Okay? So give the name of a piece of equipment that you need to connect to the oscilloscope so that we can detect sound waves. So sound waves are the opposite of microphones. You put the vibration into the microphone and it produces an alternating current, which can then be detected using an oscilloscope. And once you've got the alternating current going in, you can see the trace as I've drawn it onto the screen. A sound wave has a frequency 250 Hertz, so that's what the microphone will detect. Okay, so you can work out from this equation that the period is 1 over the frequency, so the period should be 0.004 seconds. And since they told us that 1 square is 0.01 second, there's 1 square, 4 of those will be 0.04 seconds. So the period of this wave will be this much. But of course the oscilloscope will be able to detect 2 of those waves across the screen. I didn't quite go to the same peak as a red line that I drew before. And that's why I draw them before, so it's quicker to go through the run-through with the depth that I go into. Okay, so complete the diagram by drawing the trace that as I've drawn it. So my red line will draw it because they said the amplitude is 4 volts. So on an oscilloscope, the amplitude is in volts because you're basically looking at an electrical signal, in this case created by a sound wave using a microphone. Okay, so 5 marks, you'd have to look at the mark scheme because I haven't analysed how you get the marks. Okay, this is very likely to come up again in 2025. Something similar using oscilloscopes. So you need to know how to read the oscilloscope settings. It comes up very, very commonly. Part C then says the graph shows the wavelength, how it varies in air with frequency. Well, we know if the wavelength goes up, the frequency goes down and vice versa. So the wavelength is in meters and the frequency in hertz. Okay, so they are inversely proportional because we know V equals F lambda. And we know that for the sound wave, if it's in air, we know the sound wave is always constant in air of 340 meters per second. So if frequency goes up, then wavelength must go down by the same amount. They are said to be inversely proportional. If they're inversely proportional, then when you multiply the values from the graph, they should give you constant values. It's the same as Boyle's law. P1V1 equals P2V2. That means if you take one point of the graph, lambda 1 frequency 1 should equal lambda 2 frequency 2. And I chose 2 points carefully to give me nice easy values, 0.1 3.5 and 100 frequency, 0.2, 1.0, and 350. If you're good mathematically, you'll see that immediately those two will come up with the same answer. So if you've done it twice, you get 2 marks. And then you say, since both points equal the same answer, both points are constant, that means wavelength and frequency are inversely proportional. So when you have inversely proportional variables, if you multiply them, they give you the same answer. So they could ask you a question like this. This is the last question of the paper, so we've finished the run-through. They could give you a question like this using Boyle's law, because they haven't given you anything on pressure yet in paper 1. So that's the final run-through. And here's the final mark scheme. Microphone, the trace, a double trace. Yes, the period is there to there, as I explained. And you need to know how much each square is worth. 4 periods equals 0.004 seconds. Okay, and that is the end of the run-through. So I hope you found that useful. Don't forget to show your support by liking each video. And I'm going to show you the questions that were covered. So in red is what we saw in this paper. We used this. We used acceleration. And I'm saying in 2025, they're likely to use this because it hasn't been used yet. We used F equals ma. Yeah. I think they're going to use this with specific capacity. They're going to kill 2 birds with 1 stone. Yeah. They're going to do the energy input electrically and measure the temperature rise with specific capacity. That's one of my predictions. They also haven't given you these equations, which I haven't mentioned. These haven't been used in paper 1. I reckon they're going to possibly give you an electricity question with one of these in there. Or it could be static electricity, which we haven't seen very much of. Okay? So be warned about static electricity. Yeah? So static phenomena. Okay, and don't forget that you need to know what kilovolts means, what megavolt means, and all things like that. And we've already used these equations today, and I think they're very likely to be used again with the oscilloscope question. I think this did come up before in paper 1. Yeah, and I think this did too. But you do need to make sure you revise everything. But I'm telling you what I think they must ask you. Yes, and half-life. I haven't mentioned half-life. They will ask you a question on half-life if you look at my prediction video. Radioactivity doesn't have any equations. So they also asked us about kinetic energy. They haven't asked us about potential energy or work done. So this could be a 2025 question. Okay. I think they mentioned, they did a density question, I think in paper 1. Okay. But this is my big prediction, is they're going to ask something about pressure. They could ask you any of these equations, so you need to make sure you revise those. Okay. And then finally, half-life. They're going to give you activity against time, and they want you to be able to measure the half-life. Okay, I'm pretty sure they're going to do that in 2025. Okay, it certainly is one that you should be prepared for. This is paper 2. We have done momentum, and I think it's possible that it will come up again. And they haven't done moments. So it didn't come up last year. So is it going to come up this year? And remember, 2025, also I said specific capacity. Transformer calculations are possibilities. Astrophysics, they did mention something like this in paper 1. The Doppler effect. I think they could link this with the evidence of the expansion of the universe. Like, how do they know the universe is expanding? Well, they know partly because of the Doppler effect, that distant galaxies are moving away from us. So the shift in wavelength is positive. That means the wavelength gets greater. So these are things that I have predicted. I hope you find that useful. This is the original equation sheet where they tell you what gravity is. They still include this in the inside page of the exam paper. So don't forget we use G = 10. Anyway, this is a long run through, but this gives you 2 weeks or so to prepare for your Unit 2. And if I have time, I'll upload another paper 2 as well before your exam. Okay, well, thanks very much for watching. Don't forget to like, share and subscribe. Show your appreciation, say thank you, and I'll hopefully see you in the next video. Bye for now.